Hello, we're going to start this system by giving another little shout out to Yossi. Thank you for coming every single day. I know it's going to make a difference. Now we're going to talk about number sense. So I wanted to review a few things about the real number system. There's always just like one or two little problems that go over like what type of number this is, and you have to identify the appropriate number set that a value might belong in. So let's review some of these things. The real number system is made up of natural numbers. Natural numbers consist of the counting numbers. So these are the numbers we use in every day, like 1, 2, 3, 4, 5, 6, 7. So just the positive counting numbers. Whole numbers, on the other hand, consist of all those natural numbers and the number 0. So those we consider whole numbers. Integers, these are the ones that we work with pretty much every day in math class. So those consist of the natural numbers and their opposites, and by that I mean their negatives and of course 0. So -3, -2, -1, 0, 1, 2, 3, 4, 5, etc., etc., etc. What's missing from the integers? Fractions, of course. So fractions live in the world of what we call rational numbers. We call them rational numbers because they're numbers that can be written as a ratio of two integers. So we can express them as a ratio, or in other words, fractions. So even though we have just the number 2, that's still a rational number because it can be expressed as the ratio of 2 and 1. So 2 over 1. 13/4 is 3 1/4, so that is a rational number. So is -25 over 100. We can turn that into a decimal like -0.25. So any decimal that terminates would be a rational number because it can be written as a ratio of the number over how many decimal places you have, like 25 over 100. 1/3 is also a rational number. If you think about a decimal value that repeats, that can also be expressed as a fraction, so any repeating decimal will be a rational number. So if it's not rational, it's not an integer, not a whole number, not a natural number, it's going to be an irrational number. Irrational numbers consist of numbers that can't be expressed as a fraction or an integer. They go on forever and ever and ever in their decimal place, and there is no repeating pattern to their decimals. So a couple of examples of irrational numbers would be the square root of 2, the square root of 7, the square root of any prime number. Pi is also an example of an irrational number, 3.14159, and we know that that keeps on going forever and ever and ever with no pattern. So understand, remember these different number sets so that you can classify some different numbers. We'll practice that in a second. All right, we also need to talk about exponents. An exponent, or a power, tells you how many times a base appears as a factor. So if you have an expression like this, 2 to the 3rd power, 2 is the base, 3 is the exponent, and it means multiply 2 times itself 3 times. 2 times 2 times 2. So let's go over a few rules about our exponents. First of all, powers of 1. You are all powers of 1. Just kidding. 10 to the 1st power equals 10. Anything to the 1st power is going to be itself. So y to the 1st power is just y. If you have a term written like that, you can always add a power of 1 if you need to, if you're looking at anything that has to do with exponent rules. In addition, 0 exponents always have a value of 1 for the whole term. So for example, 4 to the 0 power is 1. X to the 0 power is 1. If you had X, Y, Z, W, K, L, R to the 0 power, that would equal 1. Watch out for negative bases. Lots of times there's going to be questions about exponent rules that have negative numbers in the base, and you really have to be careful and evaluate what's going on. So I want to show you a couple things that are different. If I have -2 to the 2nd power, that means, and notice my -2 is in parentheses, that means -2 times -2, and a negative times negative is positive. So that would be positive 4. But if I have an expression like this, -2 squared, I evaluate the exponent before I evaluate the negative. It's kind of like saying -1 times 2 squared. So I do 2 times 2 first, which is 4, and then I make it negative. So -2 squared would equal -4. However, -2 to the 3rd power would be -2 times -2 times -2, and that would actually also equal a -8. So be thinking about how many times you're multiplying positives and negatives together, and whether your final answer should be positive or negative. Another thing to consider are negative exponents. They do weird things. What they do is they move a value to the opposite position. So if you have a number in the numerator, for example, if you had 4 to the negative 1 over 1, that 4 is going to move to the denominator and the exponent becomes positive. So that becomes 1 over 4 to the 1 power, or just 1/4. Or another example, 5 to the negative 3 would be 1 over 5 to the 3rd, or 1 over 125. All right, so let's practice a couple of examples of these. Let's classify each number. Negative 5 would be an integer, and it would be a rational number because I could write it as negative 5 over 1. The square root of 7 can only be thought of as irrational. I think there's 2 R's there. There we go. 2, whole number, natural number, rational number, integer. 3.145159265. We talked about this one. This is really pi. That's irrational. All right, let's simplify each of these. 10 to the 4th power. Remember, that means 10 times 10 times 10 times 10. That's 10 with 1, 2, 3. Well, it's 1 with 1, 2, 3, 4 zeros. 4 zeros. 10,000. Negative 11 squared. Negative 11 times negative 11, positive 121. What if you have a fraction squared? No big deal. 1/5 times 1/5. 1 times 1 is 1. 5 times 5 is 25. 10 to the negative 5th. Remember, we make that 1 over 10 to the positive 5 power, which is, 1 with 5 zeros. Cool. Finding the nth root of a number is the inverse of the number to the nth power. So what do I mean by inverse? Roots undo exponents. So if you have something like this, where we have n little root x equals a, that means the nth root of x is equal to a. And that's true if a to the n power is equal to x. So let's think about what I mean here. When I have a square root, it's implied that that little number in there is 2. The square root of 64 is equal to 8 because 8 squared is equal to 64. So that root undoes a square. The square root of negative 25 does not exist. We can't take square roots of negative numbers, so don't be fooled by those. Cube roots. The cube root of 8 equals 2. This is saying what number times itself 3 times equals 8. And of course, 2 times 2 times 2 equals 8. Most of the time, in my experience, what I've seen with square roots, you're going to have to be able to take some square roots, but you're also going to have to be able to order some different numbers, and square roots are going to fall in there. So, a lot of times you have to figure out between which 2 integers does a value like the square root of 52 lie. Well, let's think about the square root of 52. I know that 7 squared is 49. I know that 8 squared is 64. So the square root of 49 must be less than the square root of 64, and the square root of 52 must fall somewhere between the square root of 49 and the square root of 64, because 52 is between 49 and 64. So that means that the square root of 52 must be somewhere between 7 and 8. And because 52 is closer to 49, I would suspect that the square root of 52 is closer to 7 than it is to 8. Okay, number sets. What you need to know here is the difference between a finite and an infinite number set. So a finite set has a countable number of elements. So it only has a fixed value of how many things could be in this set. So for example, if I had a set D and it was defined as days of the week, well, there's only 7 items in that set: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. If I had a set E, which was positive numbers less than 50, well, again, there's only a fixed number of items in that set. All of the numbers between 1 and 50. There's 50 items in that set. An infinite set, on the other hand, has an uncountable number of elements. So if I had the set O, which I defined as odd numbers, well, there's an infinite number of odd numbers, right? They go on to infinity. Even though it's not all of the numbers, there's still an infinite number of them. Or the set I, integers. There's an infinite number of integers. They keep going up, they keep going down. Additionally, you need to know about the empty set. So the empty set has 0 elements in it. It is still a finite set because it has a countable number of elements. It can be written like this, where you have 2 brackets with nothing in between, or more often you'll see like the little circle with the slash through it. That means an empty set. Different than a 0. Sometimes people write 0 like that. I don't, because it's confusing. But you can see an empty set written that way. So for example, if we had the set M, which was defined as months with more than 33 days, there's no months with more than 33 days. So that would be an empty set. Here's another example. This notation is kind of weird. When I write X colon, it means I want the set of numbers X where X is less than or equal to -2 and X is greater than 5. Well, think about it. Here's -2, here's 5. Are there any numbers that are both less than -2 and greater than 5 at the same time? I don't think so. So this set would also be the empty set. There's no values that satisfy that condition. Okay, great job. Get ready to practice. Do these quickly. Get in, get out. Keep studying.